In today's video, we are talking about alkanes, the simplest organic structures. Now, first we're going to go over just hydrocarbons in general, which are anything with these CH bonds. Let's just walk through the different types of hydrocarbons first, and then we'll dive a little more in detail with alkanes. So alkanes have this ANE ending. The formula is CnH2n plus 2. So let's just take an alkane that we've seen before. Let's just take ethane. So you see that we have two CH3s and they're bound together by a carbon-carbon single bond, which we know is an sp3 hybridized carbon. See here that the formula here is C2H6. So 2 times 2 is 4 plus 2 gives us 6. Now, the reason I'm bringing this up is because as we go down our list, you're going to see that they're very similar. An alkene, very similar to an alkane, but the only difference is that we have a pi bond. Okay, and so one of the sigma bonds plus a pi bond is going to give us this double bond. So let's just draw a basic alkene. Here, I'm going to draw one butene. We'll talk more about the naming in just a bit. But the key here is that when you name an alkene, you should have an ENE naming. Up here, I said that we have ethane. And so this ANE ending is indicating that we have an alkane. Now, if we go to an alkyne, this has a triple bond. And a triple bond consists of a sigma plus a pi bond. Remember that pi bonds are formed from p orbitals, okay? Pi bonds are formed from p orbitals. So let's just draw ourselves a simple alkyne. Here I have one pentyne. Again, we'll talk about the naming in just a minute. What I want to highlight here is when you name an alkyne, you have that YNE ending. And one of the key things I want to bring up is drawing an alkyne. Now, notice here that we have, it almost looks similar to this alkene that we've drawn, but we know that we have 5 carbons here. I'm going to count this out. 1, 2, 3, 4, 5. So for an alkyne, each of the ends of that triple bond have a carbon. So there's a carbon here. Okay. That carbon's bound to a hydrogen that we're not showing. Here's a carbon. And then remember that every vertex for these skeletal drawings has a carbon. I want to also highlight for alkynes, don't do the following. So alkynes we know have sp hybridized carbons. So we don't want to draw, let's say we wanted to draw something with 1, 2, 3, 4 carbons. This would be incorrect. This carbon here at carbon 3 is not linear. And we know that those triple bonds are formed using an sp carbon. We know that that must be linear. So to draw an alkyne with only 4 carbons here, this is signifying that we have these 4 carbons. There's a carbon here on the alkyne and here. Alkynes are always linear, so don't draw them bent. All right, and the last type of hydrocarbon is considered aromatic hydrocarbons. This is outside the scope of this video, but just know that aromatic hydrocarbons have very special properties in that they're aromatic. They're also flat. These have extended pi conjugation. The one that I've drawn here is benzene, and you might have heard of that before. But benzene is also toxic. Just a little side note. Again, in this video, we're going to be focusing on alkanes. Now let's look at some of the properties of linear alkanes. So here I have names of alkanes, and you'll see that the formula here is just increasing by 1 carbon. Now remember our formula was CnH2n plus 2, and so you'll see that the number of hydrogens are also increasing. Notice here that each of the endings have that ANE for an alkane. So methane has 1 carbon, ethane has 2, propane has 3, butane 4, pentane, pent 5, hexane has 6, right? Hexagon has 6 vertices. Heptane has 7. Octane has 8. Nonane has 9. Decane has 10. You could probably stop at around, I don't know, maybe decade, unless you want to be the life of the party, and then you can learn what isocane is. Now, once you get to isocane, that's when it's kind of cool. You end up getting a solid. These are linear alkanes with a whole lot of carbons, okay? What I want to do is look at the densities and look at what state these linear alkanes are in. So up to about 4 carbons, you're going to have these linear alkanes in a gas, so up to about butane. Then they start to become liquids. Now, the main difference is that you're adding carbons, right? So the molecule's getting larger, and that makes sense that it's going to be less likely to be in its gaseous form. One of the things you'll notice, though, is the density is quite low. Let's compare the densities of these to water, which we know is around 1 gram per centimeter cubed. And so linear alkanes are much less dense than water. They are less dense than water. Now, another thing about alkanes is that these structures have simply CH bonds. We don't always draw in the hydrogens, but they are there. Now, the electronegativity difference between a carbon and a hydrogen is very small. And also the electronegativity difference between 2 different carbons is 0. Okay, so these linear alkanes are what we consider non-polar. Now, if we compare it to something like water, we know that water is very polar. The oxygen here is very electronegative, and so our dipole moment is going to be moving towards the oxygen that wants those electrons. And so whereas water is polar, linear alkanes are nonpolar. This means that they do not mix. If we go back to our density example here, comparing water and linear alkanes, again we see that water is more dense than linear alkanes. And if they don't mix, this means that linear alkanes sit on top of water. And this makes sense when you think about oil spills in the oceans, or if you're cooking and you use quite a bit of oil, sometimes you'll see that film on the top of your pot. So it's pretty neat that we can just look at the properties of linear alkanes and understand these phenomena. Why do oils lie on top of water? Well, they're just not as dense. And the reason they don't mix is because alkanes are non-polar. Another thing I want to bring up is that if you get to much higher numbers of carbons, you end up getting these solids. And the reason I bring it up is because we have things around us that have these alkanes. So for example, here's some lip balm. And lip balm is used to create a protective surface on your skin, so that way it doesn't dry out. And the way that they do this is there's actually linear alkanes in this. Seriously, you can look at different lotions and such to see. Let's see, this one has hydrogenated poly C6 to 14 olefin. That means I have linear alkanes. Now, this is a polymer. However, there's a lot of linear alkanes, and it makes sense because this is not liquid. This is solid. And so alkanes we have and use actually in our daily lives as well. Now, of course, we aren't just going to be looking at linear alkanes. Our structures are going to be more complicated than that. And when they have groups attached, these groups are called substituents. Okay, substituents is a title that I'm going to use a lot, and it depends on what the functional group is or whatever is attached there. And I want to talk specifically about alkyl groups. Notice here I don't have alkane groups. It's not alkane groups, it's alkyl groups. This is when it's attached to something. So let's just take, for example, let's take pentane. 1, 2, 3, 4, 5. I have 5 carbons, and the way that I know that is I can just count the vertices here. Okay. When you draw skeletal structures, you usually do an up-down fashion, okay? Now, if I were to draw, let's say, a methyl group coming off of this pentane structure, let's put it here on the 2 position, okay? I don't have to draw CH3 to indicate that there is, in fact, a carbon with 3 hydrogens there. Or you could, if you'd like. But this is the same as me writing this, okay? which is also the same as me writing this. But organic chemists are lazy, so we would rather just draw this, okay? So this is 2-methyl-pentane. I have my base structure of pentane, and the methyl is a substituent. Notice we replace the ANE with YL. Here I have listed different alkyl groups, and it would be useful for you to go through and see if you understand their connectivity. Let's take another example. Here we've got an N-butyl group. Now notice there's different ways that you can combine 4 different carbons. So we have sec-butyl, and we have isobutyl, and we also have tert-butyl. So another way to draw these would be simply 1, 2, 3, 4, okay? And here I'm drawing a squiggly line indicating that this N-butyl group is attached to something else. And so we would call this N-butyl because it's a substituent. It is attached to something else. Tert-butyl would have 3 methyl groups on a carbon. There are 4 carbons total. So you're going to hear me refer to these substituents as just their alkyl group name. So again, remove the ANE and then you're going to add a YL. Let's go ahead and dive into some of this nomenclature. And you are now going to be part of the International Union of Pure and Applied Chemistry. All that means is that you can now talk to chemists all over the world about different structures. There has to be some kind of a process and terminology. Otherwise, people are going to be calling things different names. So let's just walk through nomenclature for alkanes. And this is really applied to all chemical structures. The first thing that you're going to do is you're going to count the longest alkyl chain, and this is going to give you the parent or the base of your compound. So on this example, 4, 5, 6, there are 6 carbons here. So our base name here is going to be hexane. The second thing you're going to do, label your substituents. In our case here, we have 1 methyl group. So we're going to put methyl in front of hexane. Okay, so methyl hexane. And then the last step, step number 3, is you're going to indicate where. Where is this methyl? And you're going to use the lowest numbering scheme. And what do I mean by lowest numbering scheme? Well, as I look at this, our methyl is on carbon 2. So this would be 2-methyl hexane. Now you could imagine that I could count it the other way. 1, 2, 3, 4, 5, 6. This would give us 5-methyl hexane, which isn't correct. You always want to use the lowest number. So if you count it like this, you'll simply look and notice that, oh, I could start the 1 where the 6 is. So let's do another example together. So the first thing here is we need to count the longest alkyl chain. 1, 2, 3, 4, 5. Cool, we have 5 carbons. Second is label the substituents. Well, here we have 2 methyls as well. And the third is indicate where by using the lowest number. And luckily I counted this correct. So we've got 2 methyls on the 2 position. So we decided it was pentane because there are 5 carbons. We have 2 methyls, so we're going to write dimethyl here. YL. And then we have to indicate where these methyls are. And in this case, they're both on the 2 carbon. So you're going to write 2, 2 dash dimethyl pentane. If our methyls were on the 2 and say maybe the 3 carbon, it would be 2, 3 dimethyl pentane. Later on, we're going to be talking about more complex structures, and these are going to have names of substituents that are a little different, again, from their base parent or their element. In this case, Br is equal to bromo. Cl, a chlorine, is equal to chloro. Fluorine, this would be fluoro. Iodine, iodo, etc. So in this case, let's go ahead and label our parent alkyl chain. We've got 4 carbons. That would be butane. And then our bromo group here is on the 2 position. So this is going to be 2-bromo butane. Pretty simple. The key of knowing this is so that way you can understand and communicate to others what organic compound you are looking at. I want to talk about something really important, and this is something that will come up a lot. When we look at compounds, we have to understand their relationship. All right? We have to understand that one compound, how can we describe that compound in comparison to something else? The first one we're going to learn is constitutional isomers. Isomers in general have the same molecular formula. In particular, constitutional isomers just mean they're connected differently. So let's write that out. They are connected differently. The way I remember that is that constitutional isomer starts with a C, and so does the word connected. Connected differently. They have the same molecular formula. So let's take our 2-methylhexane example from before. So this is 2-methylhexane. Now, in order for us to draw a constitutional isomer, essentially we just have the same number of carbons and the same number of hydrogens, and we just have to connect them differently. So you could imagine drawing something where our methyl group is now coming off of the 3 position. This would be considered a constitutional isomer. Another term that you're going to hear me use a lot is conformations. Okay. Now, conformations are the same molecule, and typically they're just rotated differently. The way I remember this is conformations has this R in it, so rotated differently. That one's a little bit of a stretch, but let me show you what this is. So if I have 2-methylhexane, I could also draw this where I'm rotating one of the carbon-carbon single bonds. Now it's going to look a little weird, but it's still correct. If I rotate this bond here, I still have the 6 carbons that we talked about. So we still have the same compound. It just looks a little different. These are just conformers of each other. And this is simply just rotation that shows something that looks like a different molecule, but it's still the same. Remember that when we look at compounds, we're really looking at how they're bonded, where they're bonded, okay? This still gives us this 2-methylhexane. It's just rotated differently. And we're going to talk more about conformations and why molecules, and especially linear alkanes, are drawn like we have up here at the top and not like this little wonky structure down here, okay? I want to go back and talk a little more about the properties of these linear alkanes because there are physical properties that apply to all molecules, really. When we look at the boiling points of alkanes that we've learned about, we see that they increase when you have more carbons, and that makes sense because you have essentially made the compound larger. So if we just look at hexane, also this is typically denoted as N-hexane, just saying that it's a simple straight linear alkyl chain. This has a boiling point of around 69 degrees. Now, if we were to take a constitutional isomer of hexane, and let's make this a pentane base chain, and let's put the other carbon here on the 2 position. So this would be 2-methyl YL, right? Pentane. The boiling point of this is actually lower. The boiling point is around 63 degrees centigrade. Now, the difference in boiling point doesn't make sense if it's just based on the number of carbons. And so this is involving one of the intermolecular forces that you may have learned about or we're going to be using in this course some too. So these are van der Waals forces. So this is an intermolecular force. This ER just means you have two molecules interacting. And what's happening here is that if we have a pot of hexane, what's happening is that this will boil at 69 degrees, and it takes more energy for it to boil because of these van der Waals forces. Remember how we've talked about how these carbon-hydrogen bonds are not simply just straight lines. They're actually orbitals with electrons floating around in them. These are going to interact with each other. If we have a straight chain alkane like N-hexane, these forces are going to be able to line up. There's more surface area for the N-hexane to line up and have this weak van der Waals interaction. So we have all of these nuclei, right, in our N-hexane. We also have these electrons that are floating around. So think of it kind of like this globular chain of positive and negative charges. And so when it interacts with another globular chain of positive and negative forces, or another N-hexane, these are going to interact, and this is why the boiling point is actually larger than 2-methylpentane. That's because the surface area for this 2-methylpentane is smaller than N-hexane, which is in a nice linear form. And I can show you this with other examples of constitutional isomers of hexane. Let's draw another one. Here I have 2,2-dimethylbutane. And the boiling point of this is around 50 degrees centigrade. And this makes sense because 2,2-dimethylbutane doesn't have as much surface area as our N-hexane does. And so the interactions here are weaker between molecules. And that makes it easier for us to boil them and separate them into a gaseous form. There's one other thing I'd like to highlight here. When we have a carbon on this end of this N-hexane, we would consider this a primary carbon. So primary carbons have just one other carbon bound to them. Let's look at another example. Let's do a secondary carbon. On N-hexane, this is considered a secondary carbon. It has two carbons bound to it. You can also have tertiary carbons. 2-methylpentane has a tertiary carbon right here. This thing has 3 carbons bound to it. So this carbon here is a tertiary. And the last one would be if there were 4 things bound to a carbon. This would be a quaternary. And we have one on this 2,2-dimethylbutane. The key here is when we use these primary, secondary, tertiary, or quaternary, we are looking at anything that is not a hydrogen, okay? We understand that in N-hexane, this primary carbon does have 3 hydrogens. It has 4 things bound to it, but we're only looking at things that are non-hydrogens. The reason we use this naming is, again, so that we can effectively communicate with our other chemists. Okay, so essentially this is just another piece of the puzzle as we're learning the language of organic chemistry. You're going to hear me refer to them quite a bit. Here's a primary or secondary carbon, right? Or this secondary carbon is rotated this way. So just start to get acquainted with using this primary, secondary, tertiary, or quaternary terminology. Let's go around and let's name a couple others. So here on this 2,2-dimethylbutane, these 2 N carbons, what are they? Well, I already kind of gave you a clue. These are primary because I drew it with red. 2,2-dimethylbutane also has a secondary, and we can do that one too. Here's a secondary carbon right there. Again, this is just another naming technique that we can use to describe and coordinate with other chemists as we look at molecules. One last piece of our puzzle here. We talked about constitutional isomers. Now, one of the things we have to get good at is looking at a molecular formula and being able to think about what molecules would satisfy that molecular formula. The key to doing this is we need to understand how many double bonds or rings are present when we just look at the molecular formula. This is the first piece of information that you can gain from it. So if you were given C3H6O and you were asked, draw constitutional isomers for it, you could go ahead and just guess and check. But we're going to at least learn this formula. It's going to make it that much faster and easier, okay? Double bond equivalence is essentially taking the number of carbons plus 1 minus the number of hydrogens over 2 minus the number of halogens over 2 plus nitrogens over 2. When you do this, you do not count oxygens or sulfurs, okay? So let's go ahead and do this DBE for C3H6O. We've got the number of carbons, which is 3, plus 1, minus the number of hydrogens over 2, 6 over 2. We don't have any halogens, so this would be 0 over 2. And we also don't have any nitrogens. Okay, so we've got 3 plus 1 minus 3. This will give us a DBE of 1. This helps us a lot. So double bond equivalent is either a double bond or it's a ring. So for example, if we have a structure with one alkene, this would have a DBE of 1. If I have a ring, this would have a DBE of 1. And you can count your carbons and hydrogens and see if that's true. What if we had a carbonyl? This would have a DBE of 1. There is one pi bond. So we're just really looking at how many pi bonds or how many rings. This epoxide would have a DBE of 1. It has a ring. So knowing this information, this makes it really fun. This is a place where we can be kind of creative on how we can put together 3 carbons, 6 hydrogens, and an oxygen and draw different constitutional isomers from this molecular formula. Then I look at what other atoms are present. Well, I have an oxygen, okay? So I could put the oxygen here in the end or in the middle. Those are our 2 options. Now I have 1 degree of unsaturation. And so I could either draw a double bond maybe on the carbons or with the oxygen. And so let's draw it here on the oxygen. These are 2 constitutional isomers of each other. The one on the right here is actually acetone, and that's present in nail polish remover. Here we have an aldehyde. Now let's try and figure out another way that we could put this together. Well, we talked about how rings could also be double bond equivalents. This epoxide has 3 carbons, an oxygen, and 1 ring. So there you go. There's another constitutional isomer of C3H6O. There are tons for this one. We can keep going. You can have just simply a pi bond, and then you can have an OH group coming off of here. This would be an alcohol. We still have our 3 carbons, 1, 2, 3. We have our oxygen, and we have 1 double bond. Now you can always go back and count all of your hydrogens, but it makes it a lot faster when you know how many double bonds or rings are present. So you don't have to count all of the hydrogens every time. Why don't we do another example together? And I want you to try this on your own. So first, go ahead and calculate the DBE for C5H9N. Go ahead and pause the video, and then we will go over the answer together. All right, let's do this. So we've got 5 carbons plus 1 minus 9 over 2. We don't have any halogens, right? So 0 over 2 plus, hey, we have a nitrogen, plus 1 over 2. Okay, so 5 plus 1 is 6 minus 9 over 2 plus 1 over 2. 6 minus 8 over 2, which is 6 minus 4. I'm writing this out a little more because it's super simple to mess up your addition of fractions. So anyway, we've got a DBE of 2. Well, this is kind of neat. Now we have a nitrogen and we've got 5 carbons. What I like to do again is I like to kind of start out with just my alkyl chain, and then I'll put my nitrogen somewhere. So we could just start it here in the end. Now I know that nitrogen always needs 3 bonds. So we could go ahead and do that. We could put our two hydrogens here on this nitrogen, but I need 2 double bonds, right? Okay, so a simple way to do this would be to just draw 2 double bonds in. Now notice here how you can't just do this. That would mean that this carbon has 5 bonds, which is wrong. So you have to be careful as you're starting to draw your constitutional isomers of what's allowed. Okay, let's look at some other options. Now, there's so many answers to this, so it makes it really fun. Another way that you could do this is you could put both of your double bond equivalents on the same functional group. Well, how do I do that? Well, 1, 2, 3, 4. You could still have the nitrogen here on the N and essentially have this triple bond. And this is what's called a nitrile. So as you can see here, we've got 1, 2, 3, 4, 5 carbons and a nitrogen and 2 double bonds. Notice here again that the triple bond is linear, okay? So again, don't draw that bent. We do have a carbon here at 5. There's a carbon right there. You could also draw a ring. All right, with a nitrogen here. But now we do need a double bond. We need 2 double bond equivalents, and our nitrogen always needs to have 3 bonds there. Okay. There would be another constitutional isomer. You could also just put a triple bond, a carbon-carbon triple bond at the very end. 1, 2, 3, 4, 5, and here's our nitrogen. So there are a lot of different possibilities when you're looking at constitutional isomers. So in this video, we went over a lot of different terminology. Now we have focused on linear alkanes, but these are terms that will be brought up again and again and again. Okay? Constitutional isomers just means that they're connected differently. It's the same molecular formula. You now know how to take a molecular formula and figure out how many double bonds, how many rings are present, okay? Then we also discuss properties of linear alkanes, but this is applied to a lot of different molecules. These intermolecular forces of how molecules interact with each other can change physical properties, and we'll start to discuss different types of intermolecular forces in future videos. So that's it for our intro to alkanes, and I will see you in the next video.